In the last lecture, we were discussing the separation of variables procedure for solving unidirectional transport in a Cartesian coordinate system. Okay. So, just briefly, a channel in which at the bottom the z star is equal to 0, on top z star is equal to 1. The boundary conditions are T star is equal to 1 at the bottom, T star is equal to 0 on top, and initially the temperature is uniform throughout, equal to the temperature of the top surface. T star is equal to 0 at initial time. Okay. And we had defined scaled distances, scaled temperatures and scaled time, and once we did that, the solution, the equation became independent of any parameters. Okay. The equation became independent of any parameters. The boundary conditions were also independent of parameters. If we chose the channel width for the z coordinate and the diffusion time over a distance h for the time scale. First we got the steady temperature. Okay. At steady state, the second derivative of temperature is equal to 0, and therefore temperature is a linear function. And then we had defined the temperature as the sum of a steady part plus a transient part. Equation for the transient part is identical to the equation for the total temperature. Okay. The boundary conditions for the transient part are T star is equal to 0 on both surfaces. Okay. The transient part of the temperature is equal to 0 on both the top and bottom surfaces, homogeneous boundary conditions. Okay. You recall that I had said that we have to reduce it to homogeneous boundary conditions in the spatial coordinates. And at initial time, the temperature is, the transient part of the temperature is equal to the negative of the steady part of the temperature. Okay. So, and then we had solved it by separation of variables, express temperature as a function of time times a function of z. The solution in time is exponential. The solution in z is sine and cosine functions. Okay. In time it has to be exponentially decreasing, so that the transient part goes to 0 in the long time limit. In the z coordinate, the solution are sine and cosine functions. One constant b has to be 0 because the temperature is equal to 0 at the bottom surface. The condition that the temperature is 0 at the top surface also gives us a specific set of values for this parameter b. The parameter b can be I times pi, where I is an integer, so that the sine function goes to 0 at the locations where beta is equal to I times pi, and therefore the boundary condition is satisfied. Note that we got these discrete values only because the transient part of the temperature was equal to 0 on both surfaces. Okay. Had the transient part of the temperature not been 0 at the top surface, we could not have got these discrete values for beta, where the temperature, the transient part, has to be equal to 0. Okay. So, with that, this is the final solution for the temperature profile, which contained a constant AI, that was the constant of integration. This temperature solution satisfied the conservation equation and the two spatial boundary conditions, and we had to determine the coefficients AI from the condition that the transient part of the temperature has a specific value at t is equal to 0, has a specific functional form at t is equal to 0. That is, this is the equation from which we had to determine AI. Okay. Effectively, from this one equation, we had to determine an infinite number of coefficients. Okay. So, this, the left side is a summation and it contains an infinite number of coefficients in principle. The right side is just a function, and from this equality we had to determine these infinite sets of coefficients, which seems infeasible, because you cannot determine an infinite set of coefficients from just one equation. However, in this case we have what is called the orthogonality condition. Okay. That is, if I multiply both sides by sine of j pi z, okay. If I multiply both sides by sine of j pi z, where j is also an integer, and integrate over 0 less than or equal to z less than or equal to 1. Then we saw in the last lecture that the left side is non-zero only when I is equal to j. Okay. This integral on the left side is non-zero only when I is equal to j. In other words, these functions sin I pi z and sin j pi z, when integrated from 0 to 1, are orthogonal to each other. Okay. The integral is non-zero only when I is equal to j, and it is equal to 0 whenever I is not equal to j. Okay. So, that was the orthogonality relation, okay, the orthogonality condition for the left side. And therefore, since it is non-zero only when I is equal to j, the left side is just equal to aj. Okay. So, the summation of ai times delta ij. Kronecker delta is non-zero only when I is equal to j. Okay. So, the delta ij is 0 for all terms in this expansion except when I is equal to j, and therefore, you just get one particular coefficient on the left side. Okay. And on the right side I have minus 1 over j pi. Okay. So, therefore, the solution, okay, so this integral I had explicitly calculated for you in the last lecture. Kindly go and revise it if it is not yet clear. Okay. So, the transient part is equal to summation of, okay, minus 2 by j pi. Okay. aj, okay, in this expansion, this, sorry, let me just, okay. aj is minus 1 over, this will imply that okay, just solving for a, okay, minus 2 over I pi, I is equal to 0 to infinity, sine of I pi z e power minus I pi the whole square times t. Okay. That is the transient part. Okay. And therefore, the total solution is the sum of the steady plus the transient. Steady is 1 minus z star, the transient is minus summation of I is equal to 0. In this case, I is equal to 1, because I is equal to 0, the sine function just becomes 0. Okay. Note that for I is equal to 0, the sine function just becomes 0. Okay, of 2 by I pi sine of I pi z e power minus of I pi the whole square t. So, that is the final solution for the temperature field as a function of time. And as you can see, it contains an infinite number of terms. However, the terms for greater values of I, the terms for greater values of I, okay, are exponentially decreasing as e power minus I pi the whole square. Okay. They are exponentially decreasing as e power minus I pi the whole square. Right. So, for I is equal to 2, it will be equal to e power minus 4 pi square t, 3 will be e power minus 9 pi square t, and so on and so forth. Okay. So, these terms for higher values of I decrease exponentially. Okay. And therefore, in order to get a numerical approximation for the solution, you might consider truncating the series at some finite value of I in order to get an approximate solution in such a way that the higher order terms are smaller than the resolution that you require, the accuracy that you require for the solution. Okay. So, how does this work? Obviously, when T star is large, okay, When t star is large, obviously the exponential terms are very small, and therefore you can truncate it. Okay. So, for example, you can have a one term, just retain one term in the expansion, t star will be equal to 1 minus z star minus 2 by pi sine of pi z star e power minus pi square t star. That is a one term expansion. Okay. So, if you wanted it to be a little more accurate, you might consider a three term expansion, for example. Okay. Okay. T star is equal to 1 minus z star minus 2 by 3 pi. I is equal to 2, I get just. So, you consider a three term expansion, for example. Okay. And then if you really wanted to get a good approximation, you could for example take a larger number. Okay. So, let us take 10 terms or 20 terms, okay, numerically accurate. Okay. Let us call it a 10 term. Okay. Okay. You could get the solutions for these and then plot them and then see how they perform, okay, in different for different values of time. Okay. So, I'll show a rough schematic sketch of how these solutions look like. Okay. I'll show a rough schematic sketch of how these solutions look like. Okay. So, I'll plot as a function of z star, I'll plot the temperature. Okay. This is z star is equal to 1, this is z star is equal to 0, this is t star is equal to 1, and this is at t star is equal to 0. Okay. So, the final solution is a linear function. Okay. I am not plotting it very well here. So, okay, that is a steady solution. Okay. The steady solution is a linear function. Okay. And if you look at the solution for t star is equal to 1, okay, if you look at the solution for t star is equal to 1, it is not actually very different. Okay. So, these black lines that I am plotting are the numerically accurate solutions if you include a large number of terms in the series. Okay. At t star is equal to 1, there is not very much difference, okay, between the numerically accurate solution and the steady solution. Okay. So, this thing will be, okay, t star is equal to 1. Okay. And if I take a lower value of t star is the, I am sorry, this should be, okay, at time is equal to 1. I am plotting these solutions for different values of time. Okay. And at time t equals 1, this is the solution that you get. A little earlier, you will get a solution that looks like this. Okay. So, this will be at t star is equal to 0.3, say. Okay. And then at t star is equal to 0.1, I will get a solution that looks like this. Okay. So, let me write that here. You get a solution that looks like this, and then at 0.03 I will get a solution that looks like this. And at very early times you just increase the temperature on the top surface, and the temperature at the fluid has not changed very much. So, at very early times at T star, okay, you will get a solution that looks like this. Okay. So, I have schematically shown for you what is the temperature profile that I get, okay, at different times since the start of the heating on the bottom surface. At very early times it penetrates very little into the fluid because the heating has just started, and you get temperature similar to what you would get for conduction into an infinite medium. As time progresses, the temperature field tends towards the steady state value, okay, a linear profile. At T star is equal to 1, it is not very different from the linear profile. 0.3, 0.1, etc., it is a little more different, and so on. Now, on the same graph, I can plot for you what I get from the one term approximation and the three term approximation. Okay. So, for the one term approximation I will use red, and for the three term approximation I will use blue. Okay. What are the kinds of temperatures that I would get? Okay. At T star is equal to 1, there is virtually no difference. Okay. The one term, the three term, etc., give you exactly the same numerically accurate result. Okay. So, up to about 0.3 there is virtually no difference. Even at 0.1 there is virtually no difference between the actual result, the one term approximation, and the three term approximation. Okay. There is very little difference between these two. Okay. At t is equal to 0.1 you see a difference. Okay. The three term approximation still does well. Okay. The three term approximation that I am showing by the blue still does well. The one term approximation actually shows a difference. Okay. The one term approximation actually shows a difference. Okay. And this actually has a behavior that looks something like this. Okay. Not plotting it quite well here. Okay. Okay. And the three term approximation also gets it reasonably correct. Okay. It also gets it reasonably correct, but not quite. Okay. So, it actually undershoots a little bit. Okay. Where it fails is where t is equal to 0.03 and t is equal to 0.01. Okay. In this case there is a big difference. Okay. At 0.03 the one term approximation, the three term approximation still gets a reasonably accurate result. Okay. There is a reasonably accurate result for the three term approximation. The one term approximation actually goes negative. Okay. Actually goes negative. Okay. And at very early times both of them actually fail. Okay. At very early times the three term approximation actually shows some spurious oscillations. The one term approximation actually shows an even larger deviation. Okay. And this is expected, right, because the one term approximation that I have here, this one term approximation that I have here is basically the summation of this linear function plus this sine function. Okay. Okay, you are subtracting out the sine function. Okay. From the linear function you are subtracting out a sine function. Okay. Therefore, this will actually look something like this. Okay. This will actually look something like this at very early times. Okay. At later times the amplitude of the sine function decreases, and therefore, you get a good approximation. And that is what you see, a spurious single wave here for the one term approximation. Okay. the 3 term approximation is the sum of 3 waves. Okay. The 3 term approximation is actually the sum of a sine wave over 3 periods. Okay. So, it is actually the summation of this one plus something that looks like this. Okay. It is a 3 term approximation. So, it has this first term here, a second wave plus a third wave. Okay. So, it will be the superposition of things that look like this as well as like this. Okay. Sine pi z, sine 2 pi z. So, this will be sine of pi z, this is sine of 2 pi z, and this is sine of 3 pi z. Okay. And if you add them all together, you will get something that looks like this. Okay. And that is what you are getting in the 3 term approximation here at very early times. You are getting spurious oscillations there as well. Note that the temperature has to vary between 0 and 1. Okay. You cannot have the temperature going below 1. Okay. So, those are the errors that are incurred by this series solution if you retain a small number of terms. Okay. So, up to about t star is equal to 0.1, you are getting numerically accurate results even when you include only one term in the expansion, up to t star is equal to 0.1 in this case. The one term expansion fails and it predicts negative temperatures in the domain when t star is equal to 0.03 and t star is equal to 0.01. And when you go to still lower, t star is equal to 0.01, even the 3 term expansion does not give you accurate results. It still shows oscillations, and however, the larger expansion, that is the 5 term for example, would give you accurate results. So, the number of terms that you would retain in the series depends upon how accurate you want at early times. Okay. If you want accurate solutions up to t star is equal to 0.01, the 3 term expansion is not sufficient. You have to go to a higher number of terms. However, if you want accurate solutions only to about t star is equal to 0.1, okay, if you want accurate solutions only to about t star is equal to 0.1, then it is sufficient to include just one term in the expansion. Okay, that gives you numerically accurate results. Okay. At very early times, we can go back to our other solution. Okay. At very early times, we can go back to our other solution. So, let me just illustrate that here. So, this is the steady solution, this is the steady solution. Okay. Now, at very early times, when the penetration depth is small, okay, when the penetration depth is small, the solution will look something like this. Okay. Okay, let us say at t star is equal to 0.01. Okay. In that case, this temperature field is effectively similar to that for the conduction into an infinite medium that we had analyzed using similarity transforms. Okay. Recall that the temperature in that case was t star is equal to 1 minus error function of z by 2 root alpha t. Okay. That was the solution that we had got. Okay. So, at very early times you can use this solution. Okay. And if you actually plot this solution, okay, if you plot this solution in the limit of early time, okay, then it is very accurately captures the temperature profile even in a finite channel. Okay. It accurately captures the temperature profile in a finite channel, okay, even in the limit of very small times. Okay. So, for t star is equal to 0.01, and even in this case for t star is equal to 0.03. Okay. This solution for the temperature field into an infinite medium accurately captures the temperature profile that you actually see from the numerical solutions. Of course, when t star becomes 0.1 and higher, then it starts to fail, okay, because at that point the penetration depth becomes comparable to the channel height. Okay. At that point the penetration depth becomes comparable to the channel height, and therefore this solution fails. But at very early times this solution actually provides you with an accurate estimate of the temperature field in this domain. Okay. So, at very early times you can use the similarity solution for conduction into an infinite medium when the penetration depth is small compared to the channel width. At later times you can use a few terms in the series 1, 3, etc., and beyond about t star is equal to 1, even a one term approximation gives you accurate results. Beyond about t star is equal to 0.03, even a 3 term gives you accurate results. At t star is equal to 0.01 and 0.03, you could easily use the similarity solution for conduction into an infinite medium. So, the separation of variables solution including a finite number of terms is valid beyond a certain time. At very early times, if you keep a finite number of terms in the series, then you will get oscillations in the temperature field, okay, because you have retained only a small number of terms. Okay. You will get oscillations of this kind, okay, of either this kind or of this kind if you keep a finite number of terms at very early times. As the time progresses, these oscillations get damped out because the coefficients of the terms are small, okay, and then you get accurate, quantitatively accurate approximations for the temperature field. So, this sort of gives you a contrast between the advantages and the disadvantages of the two methods. Okay. The separation of variables with a finite number of terms is good for late times, similarity solution is good for early times, and the combination of these two can give you accurate results for all times for conduction into a medium of finite thickness. So, we will continue this in the next lecture. I will solve one more example for you to illustrate how this separation of variables technique works, and then I will come back and discuss a little bit about why the orthogonality relation worked in this case. Okay. So, I will give you a little bit of discussion about why the orthogonality solution worked in this case. So, I will continue this in the next lecture. I will see you then.